which is under IPR, which is Institute for Plasma Research in Gandhinagar in Gujarat. The outline of the talk is I'll first start with why fusion is important. Basically, it comes from the energy scenario, which naturally leads to the case for fusion. Some basics in fusion, which is basically meant for students and people who are not very much well versed in fusion. So for you, I'm sure you know much more than this. Then why we are doing ITER, and then some overview of the ITER machine, its status of its construction, the challenges that ITER faces, and finally I'll summarize. Okay, so the reason why we would like to do fusion comes from our needs for energy. Now, energy, there is a very nice plot which was done by the US Department of Energy, slightly old but very valid even today. What it plots is the annual per capita energy use in kilowatt hours versus the Human Development Index, which is published by UN every year. And you can see the countries which use a lot of energy. Of course, there are reasons because of the weather, how cold that country is. So US and Canada probably use the most of the energy because they are very cold, and energy consumption during winters goes up. But even most of the European countries, Japan, Australia, they use a substantial amount of energy, and that directly reflects in the quality of life. And also these are the countries which has life expectancy of about 80 years. Compared to a country like India is somewhere here, which has, it is an old plot. Right now the life expectancy in India has gone up to about slightly more than 60 years. And India has moved up a little bit from here. But still, if you see India's per capita energy consumption is about, this is a very recent data, which was based on 2016, about 1.12 kilowatt hour per year per person. And which is still about half of the world average, and about 1/4 of China, and about 1/10 that of the United States. So we are consuming far less energy, and that naturally reflects in the quality of life that we have compared to the other countries. And on top of that, countries like India and China have a significant problem of population. We have a huge population. So any increase in per capita consumption results into a very huge change in the total energy demand and production requirements. And so there are, in the Indian energy scenario, there are a short-term scenario and a long-term. I'll first say what is the short-term scenario. If you see today, India is producing about 77% of its energy through fossil fuel. This is a 2018 data which is published in Central Electricity Agency, and nuclear is only about between 2 to 3%. The renewable energy source is about 9%. There is some import from Bhutan, very small amounts, and hydro is about 10%. And this is a projection which the Electricity Agency made for 2029-30, which is about 10-11 years from now. This is a very challenging goal, in my opinion. They are trying to reduce the fossil fuel to about 50% and replacing a significant amount by about 35% of renewable, which is wind and solar. Now what it means is that wind and solar is, when it has to go about 35%, its installed capacity has to go much more, because wind and solar is not available uniformly throughout the year. So the installed capacity generally in wind and solar has to be more than 60% of the total installed capacity, which is quite significant to achieve. And incidentally, if you see around 2000, there was a 20-year vision plan of the atomic energy. And in that 20-year vision plan, around 2020, India was supposed to have about 15% of its energy through nuclear, which has not been achieved for various reasons. And we are right now about 3%, and it is at present it is projected to go about 4% in another 10 years. But you can see the change is total energy production, which is about 1050 terawatt hour, there is a consumption, will go up about 2.5 times to about 2.5. So even though the coal is about 50%, that is the plan, still the production will go up significantly. Now, India's GDP presently grows about between 6 to 8%. You can debate on that, but I will not go into that debate. But it has the potential to grow even 5% even at 2050. Generally, this is a statistical truth that electricity production grows at a rate of about 1.2 of your GDP. And for example, in last year, 2018, the energy consumption grew by about 7.9%. By this, India will still be producing about 50% of its electricity from fossil fuels because there is no other source available. And if you take that, then India's CO2 emission, which was about 360 million tons of carbon in 2000, it may go up to more than 2,000 million tons of carbon in 2050. And that actually is about 30% of the global CO2 emission in 2000. It is my personal opinion, you cannot sustain that. No, you will not be allowed to produce that much of carbon, first place. And secondly, you will not have access to that much of coal. The gas and oil is already dwindling. So that's why, the energy scenario in India and China is pretty urgent. We need to produce an alternate source of energy which is very energy dense and replace fossil fuel as quickly as possible, more than most of the developing countries. And this is the long-term scenario where the case for fusion comes. Now, this is a study which was done for even Western Europe, which was published in ISFND conference in San Diego in 2006. And the global plan, if you see the climate meetings, the global plan is to reduce the CO2 target to 550 ppm. Right now it is between 750 to 800 or slightly even more in some places. That is a significant amount, and if that has to be achieved, then there is no alternative but to go from an alternate source like fusion. If you want to do business as usual, produce as much of carbon as you want, then of course you can stay without an alternate source. But if you want to go to 550 ppm or less, then there is no alternative. Your wind and solar or any of the renewables will not give you that much. And this is a study which was done by P.R. Shukla, which is from IIM Ahmedabad, Indian Institute of Management, and his collaborators in IPP in Germany. And this is the same scenario for India. And if you want to do a 550 ppm, if you want to restrict, then beyond 2050, you have to go to an alternate source like fusion. There is no alternative. So the benefits of fusion, that it is very energy dense. You need a very small amount of fuel, deuterium and tritium, to produce a very large amount of energy. The resource is accessible to all. Everybody has water and earth, which basically produce lithium. The tritium is produced through neutron bombardment of lithium. So everybody has access to, and some small fraction of water that you drink in a glass is actually deuterium. So you can separate, do an isotope separation and extract deuterium. That everybody can do. And so what it means that many of the political and war conflicts which you saw in the last century or even now, which is basically for access to energy, access to oil, that will do if we replace dependence on fossil fuel by an alternate source like fusion. Fusion is very clean. There is very little CO2. In fact, the amount of CO2 you see is actually through production of components which are used in a fusion reactor. But it is very clean, and of course it has very manageable radioactive waste. You use very low activation material in building a reactor. For example, in fission reactors, isotopes like iodine, which has a million-year half-life, you virtually have to have a guarantee that you have to keep them buried deep underground or beneath the sea, which some countries do for their entire life. They can never be released to the environment, which is very difficult to guarantee. Whereas in fusion, typically you can manage with materials which has a half-life of, after they get neutron activated, about 100 years. So you have to ensure that you have to store them only for 100 years and nothing more. So that is the benefit. And if you see, this is also a self-sustainable development goal, and which is published by United Nations UNDP again, which says accessible to clean energy as one of the goals to achieve sustainable development of human life. So, and fusion is nothing new. We know that the suns and the stars, they burn through fusion basically. They burn through fusion of pure hydrogen into heavier elements. They can do very easily because of the enormous gravitational mass, gravitational pull. They can actually confine the entire mass and compress them to very high densities. In fact, if you see the core of the sun is the density is almost like stainless steel, and that is how you fuse hydrogen at those very high densities and temperatures. Whereas on Earth, you cannot produce so much of density because you don't. It is very difficult to confine. So what you do is use alternate concepts like confine it through magnetic fields. And the machine, the Tokamak, which is the most advanced of all fusion reactors on Earth, which has been through experiments, is one of the such devices. Tokamak is a Russian name because they were originally originated in the Westwall Soviet Union. It stands for Toroidalna Katushka Magnetina Camera, which basically means toroidal chamber with magnetic coils. Basically, when you fuse hydrogen or deuterium tritium, there is a little bit of mass is converted into energy, which you use. I'll show you some examples of that. For example, this is a list of this doesn't list hydrogen because hydrogen is very difficult to achieve in the laboratory. But the most favorable in that order is deuterium tritium, deuterium He3. And so on. And if you see here on the right is the collision cross section. The deuterium tritium has a peak cross section at a reasonably low energy of about 100 kilo electron volts, which is a fantastic amount of energy if you multiply it by 11600 Kelvin. Which it has been achieved that if you hit the plasma to about 40 keV. We don't need 40 keV in the bulk particles because typically in a Tokamak-like reactor, the plasma has a Maxwellian distribution. So if the peak is about 15 to 20 keV, there are enough particles about 40 to 50 keV in the tail of the Maxwellian. So they basically fuse and produce the fusion. And that is why deuterium tritium is easiest to achieve in a laboratory. Because you can achieve that at the lowest temperature, whereas it is not necessarily the best fusion reaction that can have because of this neutron which comes out. Neutron comes with a fantastic amount of energy, about 14 MeV, and about 3.5 MeV goes to the helium. And this helium is because it is again a charged particle, it's ionized, it is confined and hits the plasma itself, but the neutron being a chargeless particles escapes the magnetic field and gets absorbed in the surrounding structures and materials. So you have to cover the plasma through what is called shielding blankets or breeding blankets, and stop the neutrons and breed lithium in the blankets from tritium from the lithium. You basically have blankets with the lithium in it, and the neutrons bombard the lithium and to convert the tritium, which you use in the reaction itself. But if you see in some future life, probably you will like to have something like DHE3 or maybe even proton boron, because these are aneutronic fusions. they don't produce any fusion. Of course, these have produced some small amount because of the chain reactions, but proton-boron is an absolutely aneutronic fusion. So if you can heat that to those fantastic temperatures, you can simply burn them and produce fusion and produce no neutron. There is no radioactivity, but it is very difficult to achieve for present human life. Okay, so we have, of course, we have achieved fusion in the sense that there are thermonuclear explosions, but they are not controlled. Like the neutron, the hydrogen bombs, they are thermonuclear explosions. But it is the most challenging, challenge. The biggest of challenges for this civilization in science and technology is to achieve controlled thermonuclear fusion. And that is why what we are trying to do. Basically, this I have already said that a very small amount, about a gram of fusion, actually can aid equivalent amount of energy of about 8 tons in oil. And most of the experiments which has been done so far in fusion is based on the DT chain, the deuterium and tritium. And you heat them to about 150 million centigrade, which is about 15 keV. That is about 10 times the temperature in the core of the sun. You need a very high temperature because I will show, I will probably not show that, but basically you need to have a density times temperature times confinement time pretty high. And in the sun or the stars, the density is enormously high, I said that. So you can do fusion at a little bit lower temperature in the core, but in magnetic fusion, you need to have a temperature which is really very, very high. And then it produces and this I also say, the helium and a neutron. The helium heats the plasma itself. So for example, in fusion reactors, there is a state in which you can, stop the external heating and use the fusion helium itself to heat the plasma, which is called ignited condition, which is very difficult to achieve. ITER will try to achieve that, but that is not, it's part of its baseline. That is called ignited state, where the fusion gain becomes virtually infinite. And these neutrons, they go out. This is a chamber, Tokamak chamber, in the photo of inside of a Tokamak chamber. The neutrons, they go out and hit all the surroundings. So you cover the surroundings through various kinds of blankets, either shielding blankets or tritium producing blankets, to convert tritium into lithium into tritium. Okay, and then the heat which is generated by the neutrons bombarding the blanket, you convert them into basically they heat the blankets, convert into heat, and then through a conventional steam generator you convert that heat into electricity. So that is how a fusion-based reactor will work. Now, how a tokamak works is a basic cartoon of a picture. Is through what is called a magnetic cage. Typically in a tokamak you have the confining field is these solenoidal, basically a kind of a straight solenoid turned around into a torus to close onto itself so that the particle cannot escape. Initial plasma devices were linear, and linear machines you cannot confine the particles easily, so it has to be turned around. So that is how the Russians developed this configuration. You have this as a solenoid made into a torus. So the magnetic field closes onto itself, it goes along the axis. And then there is something called a central solenoid, which is also used to drive a current in the plasma, because you need a helical field. Because if you have just an axial field, then the plasma, the electrons and the ions, they basically go in opposite directions and escape the plasma. So you need to short circuit that through what is called a poloidal field, by driving a current inside the plasma. And this is what this central solenoid does. It is basically a transformer the primary, and the plasma is used as a secondary. So you change the flux here, and the changing flux drives the current through the center of the tokamak in the plasma. And then there are what is called these ring-shaped coils, are called poloidal field coils. They give the particular plasma shape. So in any tokamak, in modern tokamaks, you will find these three kinds of coils: the toroidal field coils, which are these solenoidal coils, Then these ring type coils, which are called poloidal field coils, and these are the central solenoid, which is used to drive the plasma. I'll just give an example of the ITER magnets in the next slide. This is the bare magnets of ITER. You can see these are the toroidal field coils. ITER has about 18 toroidal field coils. The field at the magnet is about 13 Tesla, because that is the limit of technology today. And each coil is about 17 meters height. You can see a human in there. It's enormously large size magnets. And each of them weigh about 360 tons, and there are 18 of them. And the central solenoid, which is the white part here, is about 13 meters in height, weighs about 1,000 tons. The amount of energy it stores can actually lift a whole aircraft carrier out of the ground. You can use that energy to lift it. That is an enormous amount of energy which is stored into the central solenoid to drive a current in the plasma. And then these red coils you can see surrounding the plasma are the poloidal field coils. They are very large magnets, about 24 meters. The largest ones, which is on the outside, are about 24 meters in diameter, and they weigh about 200 to 400 tons. Okay, so before that, before I go into more details of it, I will explain why I was saying brief what fusion has achieved so far. Now, this is a picture of the largest tokamak that we have today, which is called the Joint European Torus in Culham in the United Kingdom, close to London. And this in 1997, about more than 20 years back, produced shot which was in DT fusion, which produced about 16 megawatts of fusion power. And that was what is called a Q capital. I'll explain what Q is. Q is basically the output fusion power divided by the input power you need to hit the plasma, about 0.65. So that is pretty close to break-even conditions. Q equal to 1 is break-even, so you produce same amount of energy as you need to produce the experiment itself. And ITER needs to be much more than Q. ITER will attempt a Q, capital Q of 10. And this is a relative magnitude of advancement of fusion reactors compared with silicon chips as well as accelerators. For Tokamaks, what has been plotted is the product of density times temperature times confinement time. And if you see, the achievement is actually quite significant. We started with, Tokamak started in early mid-50s, and in 60s, 70s, there were reasonable machines. The T3, the Tumen-3 was a Russian Tokamak, which was the first significant tokamak to produce more than a keV of temperature in a tokamak. And then it has grown to like jet produce about 30 to 40 keV of temperatures. And that is when you produce that 16 megawatt and there is also another tokamak which is shown, which is TFTR, which was in Princeton. It has been decommissioned now. Then that also produced about 10 megawatts in 1994. So fusion has been produced. Only thing which has not been produced is you have not been able to extract energy out more than what you have done to spend to do the reaction. Okay, so this is a historical archive when jet achieves fusion power. And in fact, jet is still operating. This year, if possible, I'll go back to the previous slide. Okay, this, as I said, was actually Q slightly less than 1. This year, what jet is trying to achieve is to produce the same experiment is fairly steady state. So they will achieve the same about 16 megawatts for a very long duration, which will demonstrate capital Q equal to 1. And this was achieved, in 97 was a 16 megawatt shot, and TFTR before that produced 2 shots of 6.2 megawatts and 10 megawatts. And ITER is aiming to achieve Q equal to 10. As I said, the fusion gain in this shot was about slightly less than 1. And ITER will be the first machine to achieve a capital Q which is more than 1. Now, why fusion cost? There is a question which is this is a slide to answer the question, and why fusion is so expensive, it has to be so big. Is the fusion power generally scales. Beta is you don't have to understand it. Basically, it is a relation with the magnetic pressure by the plasma temperature divided by the thermal pressure by the magnetic pressure. And B is the magnetic field, and R is the major radius of the plasma, which is from the axis to the center of the plasma, which is basically the plasma size. The fusion power scales, unfortunately, with B to the power 4 times R cubed. So if you have to produce more and more fusion power, you have to go to larger size or larger magnetic field. Now there is a technical limit today to how much magnetic field you can go. Present technology with the niobium-tin magnets, which are helium cooled at 4 degrees, you can go to about 13 Tesla. That is the technical limit. And so you have, once you hit that limit, you have to go to a larger size. And this is why you can see that our machine in IPR is the TCV size, so which are about 1 meter cube in plasma volume. JET, which is the largest machine today, is about 80 meter cube, and ITER will be 10 times that, about 800 meter cube. And demo, this is a European demo, which will be slightly larger than a demo. Is the first reactor which each country will make, the fusion partners, which will actually put energy into the grid. That is the plan right now. They will be about 3 times ITER. And there is also a second approach, which has picked up some momentum in the last few years. In fact, MIT declared 2 years back that they have a breakthrough. In superconducting technology. There's a new kind of superconducting tapes. Is a REBCO tapes. Is a rare earth barium copper oxide tapes, which has the potential of producing magnets of very large magnetic fields. They can break this 13 Tesla technical limit today. And in fact, they have made small samples which can produce even up to 40 Tesla. And MIT has actually given a contract to an industry to make a 25 Tesla magnet, large-sized fusion-grade 25 Tesla magnet. Now, if they can produce that, it can actually revolutionize fusion, because then you can achieve the same amount of energy that ITER produces at roughly half the size of ITER at a larger magnetic field. And that will dramatically reduce cost, but of course that will not reduce your complications, because once you go to a smaller size, there are more complications, because you will have a smaller area and the neutrons, the same number of neutrons come out of a small amount of area, so the surrounding structure will get much more heat loads than present technology can handle. So there are problems, but that is how science works. Unless you have challenges, you don't do anything. Okay, again, for the size matters. For example, Tour Supra is a steady-state tokamak in France, which was is about 25. This has been named West now. This has been upgraded to a machine called West. It's about 25 meter cube of volume. It doesn't produce any fusion. JET, which is about 80 meter cube, it produces 16 megawatts of fusion with a heating power of 23 megawatts, with a total plasma duration of 30 seconds and a plasma current of 5 to 7 megaamps. ITER will have a volume of about 10 times of JET, about 830 meter cube. It will produce a fusion power about 500 megawatts, and the heating power it will consume is about 50 megawatts. That is how this ratio is about 10. So here you can see this ratio is about 0.65. That is why it produces less fusion power, consuming more heating power, whereas ITER will produce about 10 times the fusion power than what it consumes. This will have a burn time of about 400 seconds for the fusion reactions. There is a steady state scenario at about Q equal to 5, which will operate for like a reactor for very long times. And the plasma current maximum will be about 15 megaamps, which is about 3 times what JET has achieved. Okay. Now some history of ITER. It actually started, ITER actually is quite old. It started with the end of the Cold War in the Reykjavik summit between Ronald Reagan and Comrade Gorbachev. And they decided that fusion should be declassified. And there was a fantastic news for all fusion scientists, because earlier, when there was very little cooperation, of course there was cooperation, but not in this scale of ITER. And then a joint, plan to build ITER was developed. Originally, it was between the US, Russia, Europe, and Japan. They were the 4 partners. Then, after the ITER site was selected in 2001, and there were 4 sites initially was offered, and finally Cadarache in the south of France was chosen as the site. And then ultimately to India, first China and Korea joined in 2003, and India became the 7th partner in 2005. And this is meeting after the signature, Dr. Kagotkar here and with the French President and other ITER partners. And now there are 7 partners. So what is ITER? ITER is basically a unique mega science and engineering experiment for demonstrating a virtually limitless, safe, environmentally friendly energy source from hydrogen isotopes, basically deuterium and tritium, through fusion. And as I said, India became the 7th partner to join in 2005. It is at present the largest international science and technology collaboration project, and is also a unique management experiment. It also brings its own complications. And it is presently being under construction in Cadarache in the southern France, and the first plasma operations is planned in about 6 years from now. Okay, so the goal of ITER is to first produce a burning plasma. As I said, to produce a fusion power 10 times than the input power operating at Q greater than or equal to 10. It will produce about 500 megawatts by consuming about 50 megawatts, and also demonstrate a steady state reactor-like operations at Q greater than or equal to 5. So this will be, while this Q equal to 10 will be for about 400 seconds, this will be for about 4,000 seconds. So several minutes this will operate, because ultimately when you build a fusion reactor, you have to run it in a steady state. So ITER will demonstrate some of those. And why we are participating? Because we also have, incidentally, in IPR, 2 small experimental tokamaks. One is called Aditya, which was commissioned before I joined IPR. It was commissioned in 1989. It is still operating and doing good experiments, produce a lot of PhD students every year. And then we have the steady state Tokamak, which was started operations in 2012. That is when I joined IPR as a scientist for this project, SST1. It had developed some complications, but it is operating at a reduced configuration at present. But what it will do is, because ITER is a huge machine, so it will we can actually leapfrog our domestic program by participating in ITER. And also, each country, each partner in ITER contributes about 10% of ITER cost, not by giving money, but actually making components in each of the countries. 10% of that is actually made in India and delivered to ITER. But you get the intellectual property of the entire machine. So you invest about 10% and get about 100% of the intellectual property of the other systems. So that is the biggest advantage, because once fusion becomes successful and there are commercial licensing, and the technology will not be available to you. It will come at a very high price. So it is better that we get those technologies from now itself. And also, DT fusion produces 14 MeV neutrons. It has some strategic importance for us, because India has a huge amount of thorium, which at present cannot be used unless it is converted into uranium-233. So the neutrons, fusion neutrons, can actually convert into the thorium into a fissile in uranium, which can be used for fission reactors. So that is another option for us. There has been designs fusion hybrid reactors. Russia pursued that and even pursues this even at present very aggressively. And we also have plans to finally sometime cover the blanket through thorium to convert the thorium into uranium, which can be used in a fission reactor and make a small fusion device sustain a large number of fission reactors. So there are very detailed plans of these. Okay, some India's participation in the background. It started much before we joined, about 2001 to the first initial steps started. And then at that time there were Indo-US nuclear cooperation was also going on around 2005. Anil Kakotkar was the chairman of the Atomic Energy at that point of time, made a very active role. And finally, in 2005, after lots of negotiations, there were teams from ITER which came and visited IPR. They evaluated, because before a particular country is accepted as a partner, they evaluate your capabilities of doing certain components. Because ultimately, we have to make certain components in India and deliver. So they came and reviewed us. There was extensive review by a world, group of people from ITER who came and analyzed our capability. And finally, in 2005, we were accepted as a ITER partner after long negotiations. And in ITER is a very funny system. They say we pay about 1/11, slightly less than 10% each as our contribution. But the entire machine is divided into what is called work packages, and we get credit. So it doesn't matter. The entire machine cost, which was originally the 2001 cost, is divided at that point of time into various systems, and each system is allocated a certain cost, which is a ITER unit of accounting called KIUA. It is like a different currency, and when we deliver something, we only get that credit. It doesn't matter how much we spend. We can, and in fact, most of the countries actually spend much more than the actual kilo IUA converted to euros. And so India also has its shares. Each country is divided, and the machine is divided into packages. Each country divides a part of the machine, which are made in those countries' own industries and delivered to ITER site. And so there is an international organization called IO, and there are domestic agencies. So each of the 7 partners has one domestic agency. ITER India is one of the domestic agencies. And the role of the IO is to do the design and specifications and do the monitoring of technical progress, the quality control, schedule control, and finally the integration, assembly, and and the work site. The final assembly and integration on site is the responsibility of the international organization. It consists of people from all the partners. So some about 30-40 people from India in our lab and BARC and various other labs. They actually go and spend about 5 years there to work for ITER. And each country does that. Typically they come for 5-year terms. So each of the partners send their people to work at the ITER site for about 5 years to work there and do the carry out the activities of the international organization. And in the domestic agencies, like in ITER India, we do the carry out the final design, the actual contracting, procurement, manufacturing. In some cases R&D. There are quite a bit of R&D involved in many of the components. The quality control, and then finally we ship it and supply and helps the international organization in commissioning those systems. And also we have to do a fantastic amount of documentation, which normally we are not used to in our projects. ITER involves a huge amount of documentation. Now, without every component, first you have to complete your documentation, then only you can progress in manufacturing those components. And also monitoring the suppliers' progress in manufacturing, and do the quality control along with the international organization. So that is the role. Now what India is delivering to ITER is what is called cryostat. Don't forget about this WA stands for Watt Breakdown Structure. These are the particular name of that WBS. Basically the cryostat is what covers the entire Tokamak, is basically like a refrigerator, which is a stainless steel vessel about 30 meters in radius and 30 meters in height. And it is used, it is a vacuum chamber, because the magnets which are stored between the vacuum vessel here and the cryostat, they are all superconducting magnets cooled at liquid helium. And so they cannot be exposed to the atmosphere, so they have to be in a vacuum environment. So this outer cryostat, they ensure that the heat doesn't come from outside, it doesn't dissipate and heat up the coils, and they remain superconducting at liquid helium temperatures. So So this entire cryostat is India's package. Then there is something called there is a small amount of diagnostics, which are some of the extra diagnostics, beam emission spectroscopy. So these are all the experimentalists. They are developing those diagnostics for diagnosing various parameters of the ITER machine. Then something called vacuum vessel involved shielding. You will get more in the following talk, which will be given by Arun after me. And then there is a vacuum vessel involved shielding, which is basically blocks of special braided steel which goes into the vacuum vessel, which can shield also the neutrons which comes out of the machine, and also reduce the ripple of the magnetic field. They have dual purpose, basically blocks of special steel. Then the almost 50% of the ITER water cooling system is delivered by us, by India, and the rest 50% is delivered by US. Then one of the neutral beams, which is a diagnostic neutral. ITER has 4 neutral beams, 3 for heating the plasma and 1 for diagnostics, for diagnosing the helium ash. Basically, when you produce, do the fusion reactions, the amount of helium you generate is measured through charge exchange reactions, and you need a neutral beam to be shot inside the plasma at a particular energy, which do charge exchange, and you measure those ions to measure how much helium you have generated into the machine. So that neutral beam will be delivered by India. Then the entire radio frequency sources of ion cyclotron and few gyrotrons. The RF sources are all India's procurement. There is a huge amount of R&D involved in developing those particular tubes, because I'll show that in a more complicated, because most of these components are first of its kind. They have never been achieved so far in industries or any of the labs. So they have to be specially designed and developed for ITER. So this is developed by India. Gyrotrons, 2 of the gyrotrons which will be used for startup will be delivered by India. Actually, it is no longer for startup. It is both for startup as well as heating, because the frequency is about 170 gigahertz RF tubes. Then all the power supplies for the neutral beam, for the ion cyclotron heating, and the gyrotrons will be delivered by India. And the cryo distribution and cryo lines, which basically carry the liquid helium from the helium plant to all the magnets, they are all India's procurement. So this contributes about 1/11 of the entire ITER, which India is delivering. The others will be delivering the rest of the machine. Okay, so these are some of the examples of the procurement so far in my various manufacturing activities. This, for example, is the cryo line which is being developed in a company called Inox in Baroda, close to Ahmedabad, which is India's procurement. Then there are picture frame coils called correction coils. I didn't show in those magnetic field configuration. Apart from the toroidal magnetic field, poroidal and central solenoid, they are also called correction coils and name control coils. These are smaller magnets. So the correction coils are being made by China. These basically correct the errors in the magnetic fields. And then the thermal shields is being manufactured by South Korea. India has already delivered. This is after delivery. You can see a completely packed lower cryostat, lower cylinder of the cryostat, which has already been delivered. Then the central solenoid, as I said, is a US procurement, the huge magnets which is being made at San Diego in California. This is already, they have already made 1 module, and 1.5 in fact has been completed. Then there is a neutral beam test facility, which is a ITER facility, was not at Cadarache, but it is in Italy. So the Spider neutral beam system in the NBTF, neutral beam test facility in Italy, which is an European procurement, which is already in progress. Then this is one of the toroidal field winding packs. You can see the size from here. These are about 30 people standing inside a magnet. Okay, so this is the full size of the magnet. It is enormous, about, as I said, about 16 meters in height. These are the largest magnets ever produced in the world. And these produce 16 Tesla at 4 degree Kelvin helium temperatures. And this is a sub-assembly of the vacuum vessel, which is being done in Europe at present. Europe and Korea jointly produce roughly 50% of the vacuum vessel. So this is the vacuum vessel sector which is being made in Korea, South Korea, and these are being made in Europe. Then one of the TF coil magnets, that's number 7 winding packs, is completed in Europe. And again, that winding pack 12, this is one of the first magnets which will be delivered in a few months from now. In fact, in March to 2020, the first number 12 and 13 magnets will be shipped to from Japan to ITER site. So you can see the size. This is again about 30 people, and this is the size of the magnet in the casing. And then the PF6 coil, which is one of the parallel field coils, is actually European procurement, but Europe has subcontracted it to China because of schedule requirements. This has already been completely wound. This is they undergone impregnation, VPI impregnation is underway. This is one of the smallest magnets, in fact. And the PF1 coil, which is Russian procurement, is also close to completion in manufacturing. Then there are vacuum vessel ports, which is again Russian procurement. There are one of the ports which is almost ready. Then this is a what is called a diverter cassette, one of the diverter cassettes. This takes the direct conducted heat of a tokamak, which is about 20 megawatts per meter square. It is an enormous amount of heat. Incidentally, the aerospace, the re-entry vehicles which NASA uses, they take heat of about 10 megawatts per meter square. This takes much more than that in a tokamak. So there is a special kind of tungsten which has to be delivered, which can withstand 20 megawatts per meter square of heat, because that is what the ITER plasma will dump into the diverter and first wall. These are some of the water cooling chillers which has been made in Kirloskar in India. Again, the horizontal pumps are also made by Kirloskar. These have been delivered. Then there are bellows, vacuum vessel bellows, which are American procurement, but they are made in a company in Germany. This is the factory acceptance test is ongoing. And there are some of the AC/DC converters in China, which has been delivered now in ITER site. So these are just examples of how it is progressing. But also ITER has significant amount of challenges. Any R&D in science and technology has its own challenges. There are technical challenges. Like I said, almost every component in ITER is first of its kind. They have very large in size, has never been developed in such a large size. At the same time, they need enormous precision. Like, for example, I said the cryostat, which is a 30-meter size vacuum vessel, it has a tolerance of ovality of less than 10 mm, which is enormous to produce in such a large size. It needs a very new kind of engineering, very precision engineering, and those are basically technical challenges. Then there are scientific challenges. Not every physics of ITER is known. For example, ITER is a huge extrapolation in many physics parameters from the present day experiment, just simply because of its size. Some of the dimensional parameters in ITER, those are fairly technical, so I will not go into the details. They have not been achieved simultaneously in the present day Tokamaks, so the ITER will be the first time which will operate in those kind of parameters. For example, I'll just give an example. Most of the present fusion which has been achieved in JET or TFTR, they have been achieved in what is called a hot ion H mode, in which the neutral beam basically hits the ions. Though the ions are at a very high temperature, larger than the electron temperature, which is a favorable condition to have in a tokamak. Whereas in ITER, the neutral beams are so high energy because they have to penetrate into the plasma, and those penetrates, the ion-ion collision frequency is very less and cross-section is less. The ions dump most of their energy into the electrons, and the electrons further than heat the ions. But it means that you don't have the hot ions, but you have electrons and ions more or less at the same temperature. This is a completely different operation regime where ITER will operate at. So you lose some of the benefits of neutral beams actually. Then there are issues like the plasma disruption is a huge issue, and globally we have, I'm also part of that. There is an international Tokamak physics activity, or ITPA, who does a lot of experiments and modeling on how to control disruptions and runaway currents. This is a huge issue right now, and people are working in all Tokamaks and modeling groups to resolve this problem for ITER. And also how to control the very high heat fluxes. Like I said, the divertors are made with the 20 megawatts per meter square, but ELMs can give dump energy of up to 50 megawatts per meter square in short times, in pulses. So how to handle those heats by controlling the ELMs, that is a big challenge. So these are scientific challenges, those are technical challenges, and then there are management challenges. As I say, there are 7 parties with 32 nations, if you consider 26 in Europe. They have very different working culture. The working culture in India and China and in Europe or in US or Japan are completely different. They don't even say yes the same way. Okay, the Japanese will say like this to say yes. It is difficult to get all the people together for the same goal. Then the procurements are very distributed to all over the world. To maintain the same quality of components is an enormous task. Then ITER will be the first machine which will have a nuclear licensing, like a nuclear reactor, because this is going to operate in deuterium tritium, producing a lot of neutrons. So nuclear licensing itself is a huge issue. It's both technical as well as management issue. So these are some of the challenges which ITER, only one slide I can put. There are many more challenges, but I will, just to give an example, the assembly components are huge in ITER. You can see this is one of the assembly tools to maneuver the TF coil. This is one of the toroidal field coils. And you can see a human size is really tiny compared to that. Nobody has done experiments in these scales. So these are huge challenges. At the same time, they have to be positioned with very high accuracies, in watch-like accuracy. Well, this is 3D laser scanning techniques for metrology to assemble the cryostat lower cylinder. So you basically need very millimeter level accuracy in all these components, which are huge in meters. Several tens of meters. So that needs a very different kind of engineering, which we have never experienced. Our industries also are learning a great deal by just making products for ITER, which they have not done to that accuracy. Then, as I said, another challenge, management challenge, is to control the changes, because once you do a project, there are continuously some component will be changing. You change the design, there are non-conformities. There are many other changes, like even if you have to drill a hole in a building, these are nuclear buildings, it has to go through a change control process. And you can see this is a picture of the various levels of there are 5 levels of the ITER building, an enormous amount of interfaces, and everything about the others changes every time. And so they have to be, you have to make sure that it doesn't disturb the other systems. There's a complete change control, but you have to go to see everything falls into the right place. You see the number of changes which has gone over the years. It has increased to about, the peak it was about 140 changes in 2012. And each of them also cost money. Each of those changes will cost some additional amount of money. That is also one of the reasons why ITER cost has actually ballooned up a little bit. And each party, including India, they are affected by these changes. But the good thing is ITER is progressing. I had a picture, but I didn't show it. A picture prior to that. This is after flattening already. Some of the buildings have come up. This entire area was actually very hilly. This was, first of all, in around 2003, it was flattened to make a flat surface. And right now, this picture was taken early this year. If you see, it is almost, they're getting ready for the first plasma operations in about 6 years. The assembly and integration will start in 2020, first quarter. And the work site is in a pretty good shape. You can see most of the buildings are getting ready. This is the main assembly hall, and the Tokamak center is here. The machine axis will be at this point where the big crane is, and the Tokamak will be sitting here. And cryostat, which is made in a workshop, temporary workshop beyond this assembly hall, will be transported through special cranes. The ITER cryostat, which is in India is making, is the largest component in Tokamak, weighs about 1,500 tons. The base itself weighs about 1,500 tons. And to lift a component of 1,500 tons and transport it here is not a very trivial job. And you have to, and the tolerances are, as I said, in tens of millimeters. Okay, and then if you see the schedule, we are planning the first plasma experiments in about 6 years. In about December 2025 is supposed to be the first plasma experiments. And there are various phases of experiments before actually in 2035 you can start the first DT operations about 10 years from there. Because you have to establish the control systems, the heating systems. You have to basically learn a lot of things as you go along. So there will be first plasma will be in pure hydrogen. Then you start. There is a brief phase of helium plasma, hydrogen and helium. Then there is a deuterium plasma phase, pure just deuterium. There is no tritium, and the first tritium in the machine will be around this time. Before that, there is a mission service. It is the license to operate with tritium, and after that you can do the full DT operations. So about 2035, long after I retire, the first DT machine, the first Q equal to 10 fusion experiments will be there in this machine. So to summarize, the global fusion research has progressed remarkably well. ITER is the next logical step. It will be the first machine to achieve Q equal to 10 or better, which will finally lead to build each of the parties, India included, will be making their individual demo reactors. They will not be through global cooperations, because the experience you learn from ITER will help in making your own demo reactors. Demo will be the first machine which will actually work like a normal energy producing reactor, which will put energy to the grid. And for India it should come around 2050, but time will tell depending on the success of ITER how we can progress there. As I said, ITER challenges are significant. There is no science and technology mission which is without challenges, but they are being adequately handled and addressed. ITER construction is progressing well. We have completed about 65% of the construction to the first plasma as of today, as of last month. And the first plasma is scheduled in December 2025, plus minus 6 months will be achieved that date. And the first DT experiments is in 2035. That's all I have. Thank you. You can ask any questions. Yes. Yes.
You told Q equals to 10, right?
Yes.
So what is basically Q? Work output by work input?
It is the fusion power that you produce divided by the heating power.
Heating power we are installing?
There is something called install power, because basically how you heat the plasma is by injecting a neutral beam, which is basically a accelerated particle beam which is neutralized into it, because in a tokamak, because it is in a magnetic field, you cannot inject a charged particle because they are deflected by the magnetic field. So you have to neutralize those charged particles in neutral particles, but very high energy neutral particles are injected. So typically ITER will have about say 33 megawatts in 3 beams of neutral beam. So and then there are radio frequency heating. So they are like ion cyclotron waves. They are basically microwaves at a particular frequency which will resonate, because the electrons and ions are charged particles. So they resonate and as a particular gyro frequency depending on the magnetic field and the mass of the particle. Okay, and you make a radio frequency to resonate at that gyro frequency of the ions or the electrons, and then they get heated, because of the resonance they get transferred the energy from the microwave to the particles. So the particles get heated at the expense of the wave. The wave basically damp into the plasma, and so the total amount of energy you dump through either microwave or the neutral beams in ITER will be about 50 megawatts. Okay, And the amount of fusion power it will produce will be about 500 megawatts. That is how the Q equal to 10 comes.
And what's the radius of that Tokamak?
About 6.2 meters. So I didn't show that, but it's 6.2 meters. Our volume is about 830 meter cube.
And you talked about shielding blankets.
Yes.
So with what materials?
Shielding blankets are basically made of beryllium. Beryllium is a very good material to absorb neutrons. But there are also what is called test blanket, because ITER will also have to serve, show that you can breed your own tritium in a fusion reactors, because how ITER starts, to do the fusion, it needs deuterium and tritium. Right now the deuterium you can produce from heavy water. We have heavy water plants in Talcher and various other places. But tritium you have to produce at present day in fission reactors. So like the ITER tritium will come from the Kandu reactor in Canada. They have roughly about 36 kgs of tritium as of today. That is only declared tritium inventory in the world as of now. There are undeclared inventories. The bombs come through undeclared inventories. But tritium has a half-life of 12.5 years. Okay, so it will get depleted. So fusion reactors will have to generate their own tritium from the lithium blankets. So part of those blankets will have specially designed lithium targets which will absorb the neutrons and produce tritium. And it has to maintain a ratio of about 1.1 to 1.2 so that it can replenish the tritium that it consumes, plus produce a little bit extra to support a new fusion reactor.
India being a several partner of this project,
Yes.
bearing 10% of the total cost. And so far as I have understood, there is a committee from the Indian side which takes part in that project. So if a young graduate, maybe from science stream or engineering stream, want to participate in this, so what should be their approach?
That is a very good question. As I said, first of all, ITER India is a domestic agency. So we basically come from, there was a group of about 50 scientists and engineers from IPR which was selected to work for ITER. And also a group of people who go to ITER, as I said, for 5-year contracts to work for ITER. And that is not necessarily from IPR, they can go from any DAE unit so far. Okay, so there are people from BRC, from IGCAR, whichever has gone. But there is a information which is very new, it came into only in the last week. There is all likelihood that it will be open to all Indians. So even if you are not part of the DAE, there may be a time in the near future where anybody can apply for a job in ITER. Right now, for example, anybody who is not working for DAE cannot apply for a job in ITER. They have to go through the DAE route. But it will be open in future that any Indian citizen, because it is all taxpayers' money, can in principle work for ITER. You can apply. There will be some screening at the DAE level, but depending on the suitability of a candidate, a person can work for ITER. And then there are, many people, you can also do small projects like most of the labs around the world, they do work for ITER, like R&D, many basic science studies or modeling activities, which is going on around the world to support ITER. So that anybody can participate. There is no restriction on that.
Sir, you told about correction coils.
Yes.
So what are the types of error that are there in the magnetic?
Okay, you see, as I say, these are very large coils, okay, about 16 meters in height, that REF coil.
What are those correction coils made up of?
The correction coils are made of copper. Correction coils are made of copper. Just a moment. Correction coils are made of copper, you know, any idea? ITER?
The correction coils are a mix of both types. It is copper, some of them, because they are actively cooled copper.
ITER.
Most of them.
Yes.
And involving was for neutral beams and others
Yeah.
the correction coils. So they're primarily of copper.
Copper, but cooled copper, they are not.
Dedicated parts with the central
Yes.
solenoid that comes with a separate heat.
Right. So they're basically coupled coil but cooled, because you cannot put an uncooled coil into the cryostat, because the heat it generates actually heats up the rest of the magnets which are superconducting. So these are typically nitrogen cooled copper. And then there are also, I didn't show that, there are something called in-vessel coils which are installed inside the vacuum vessel, which are very difficult to make, because typically a cable of a coil is not designed to absorb neutrons, okay? But these are specially designed MGB2 coils, which are designed through Princeton and Chinese collaboration, and they will be used to make what is called in-vessel coils for controlling some of the plasma parameters. And this, I didn't complete that. The correction coils are required because when you position your toroidal field magnets or poroidal field magnets, there is always some, engineering wise, you cannot place them exactly to the absolute precision. There is always some deviation in what the ideally should be from the design parameters. So any small deviation gives a kind of error field, which is detrimental for the plasma. So to correct that, you produce those coils. To use currents in those coils. In fact, that magnetic field design itself is enormously complicated. You generate all kinds of Fourier harmonics, and each of the Fourier harmonics you have to cancel. That is why those typically the toroidal field magnets are few, but correction coils are about 9 toroidal locations, and 3 is about 27 correction coils are there. And they have to, you need a large number, because you have to compensate the higher harmonics, the Fourier harmonics in the magnetic field.
So maybe what you can have is after this second discussion, you can then perhaps have more questions. Maybe we can take it together. It's really wonderful that you have come up with this. It encourages us and it possibly gives a feel of participation. So is that okay? Can we do that later?
Yeah, thank you. So now time for, thank you.